Okay, we are back. And as I told to you on the last video, on this one, we will start to see about articulated coordinates. And as you're going to see, is a very short topic. And actually, I would just draw the robot, which is illustrated on the book with the angles which make possible its motion on the three-dimensional space. So let's get started. Articulated coordinates. Okay, so I will use the content of the book. So it consists of three rotations and following the book it says that we will get more deeply on this topic, on this subject about articulated coordinates further when we will discuss about Denavit Hardenberg. And as I said, today we will actually just draw the robot with the angles representing these rotations. So it's going to be very simple and a very short video. Okay, so we got the base, we got the cylinder, which will rotate. And we already have talked about how the geometric figure which represent the robot, which represent the way that this robot is allowed to move on the three-dimensional space. So a cylinder gives us the ability to rotate, and this rotation will change the position and will give us one angle. I think it's alpha. Let's see. It's alpha. Exactly, alpha. And is a system of coordinate with more occurrence than the Cartesian one, is a system more accurate. And when we got from the spherical one, the system it gets more, even more accurate. So we already have discussed about this. And we got the base, the cylinder. Let me draw now a articulation. Okay. And now a link, and ARM robot is what we call the whole system. It can have one link, two links. It can be simple or more complex. It depends on the robot that we are discussing, using. This one, it has two links. This one link, and this other one. Okay, very quick, huh? And for today, it's going to be all that we will do. This piece right here, it's so good. Okay, so we already has discussed this. At this point, it's good, and now you have the sense of feels because it's two-dimensional, and we are trying to represent the three-dimensional space, and even trying to represent three-dimensional bodies, figures on a 2D plane. Okay, so right here we have a axis, and we got this angle theta 2, and this is why actually um, we got the z-axis, and the z is this angle of this base of this cylinder. We're going to have actually is for the other way. Right here, right here we have this rotation, theta 1 on the z-axis, and from the base, which is fixed, we got the x-axis, and pointing on the on this direction, we can copy the y-axis coming out from the base, is the y, and as you can see on this joint we have a rotation on y-axis. So it will make this link going to down or up. It depends on the angle that we are applying on this joint. And when we apply this angle with a actuator, and this joint it goes to do a rotation. In this rotation, it will make the link going to up or to down. And on the end of the second link, we got right here. We are not drawing a 2 as the end effector, but we know that is the end effector because is where intuitively and it makes sense that we we attach it a tool on the end of the arm of the robot. So this whole system is a arm robot which is made it of joints and links. So what makes a robot arm is joints and links, and as this robot it got more complex, we will have different types of joint and links, and as well the coordinate system. So right here is the end effector, and we can represent with other reference frame. So is N A N O. Okay. And right here we got on this joint. Okay, so right here the joint is connecting the links. So right here we got this joint, and on the book is pointing to here, is drawing a arrow to here to give us this sense of three-dimensional space, but we can draw to here, and we will draw to here as well, but it's just to give us this sense of three-dimensional space. Okay, so at this point I hope you already got the sense of views of depth on a draw is important because we are representing we are trying to represent the three-dimensional space on a 2D plane, which is this blackboard. And this rotation is theta 3. Okay, on the book is not represented any transformation, but at this point, as I keep saying, we are able to write transformations because we take a reference frame and we do a transformation based on other reference frames. So let's say right here we got the reference frame fxyz, which we call universe reference frame, and also R. And I was saying because it's from robot, and it doesn't make a difference if we say that this R is from robot, or as I read on the literature, it can be from reference. So we write transformation equations because we got two different systems. reference system, and we got this other one, FNOA, and as this one we call universe reference frame, and we can say that is R, and this one we call the hand of the robot, which is the end effector. End effector. So the transformation, which is the dodo transformation, which is the transformation that tell to us where this the end effector, which is the name is already saying, is going to be at the end of the task. So this transformation is pretty much saying the whole motion that this robot is going to do, the task that it's going to perform. So right here is the end effector. We can call the end effector, and right here a universe. So we can even draw a reference system, reference frame, which is also a coordinate system. Okay, Z, X, Y. So is a transformation of the H frame in relation to the R frame, U frame, which turns into R frame. And if you has the opportunity of download the book, if you find it, or if you have access to the book, you will see that on this topic of articulated coordinates, it doesn't even bring any context as we were seeing from the other coordinate systems. Right here, it doesn't give a task, a text description, but if we assume a series of transformations, which are three, so there are three rotations, we can write is three rotations, and let's say that this is nice. Right here, let's say is Z with theta 1 and one rotation now on Y with some theta 2, and this rotation of X right here is nice because it's not pointing on the same direction as the x-axis is. It looks like it's pointing on the same direction as the y-axis, but if we do a rotation on the z-axis, and if this whole system right here on these links point to here, if we change the end effector to here, and pointing on the same direction as the y-axis, but on opposite sides, in some way we can make this axis change its position, its orientation, and actually even this x-axis, it's not defined with y or x on the book. So these angles, maybe they will change, and I'm not sure about this. But from now, let's just theta 1, which is from z, is defined. So right here is defined. And these other two, they are not defined, but we can find something like that. I don't know. And for now is all. And on the next video, I will pass to you something about inverse and forward kinematic equations. So that's it. Thank you.